looking at question B3 part 2, which is looking at electrical resistance. And I have got, this is from topic 5, so I have the data booklet at the right place for it. A reads, a resistor of resistance 1.5 ohms is made from copper wire of radius 0.18 millimeters. That will be important. The resistivity of the copper is 1.7 times 10 to the 8 ohm meters. Determine the length of the copper wire used to make the resistor. Now, obviously we are going to be using this formula over here, where this is our length. This is the cross-sectional area, and there is my resistance, my resistivity, and so forth, everything that I need. So I'm going to use that formula. I'm wanting to work out the length, so I'll just change the subject of the formula for that. The length will equal RA divided by rho. Now, there's not much to do here except that we need to work out the cross-sectional area. And in doing that, we need to make sure that we put it into the right units, because here you've got millimeters. There you have millimeters, and you have, this is in meters, so we have to make sure that that is in meters also. So your area, we take it to be a circle because it has a radius, so we use the pi r squared formula. Now that is going to be 0.18 times 10 to the negative 3 meters, and we're going to square that value to get us our area. And when I do that, let me just do that, we're going to have shift pi times 0.18 negative 3 squared. I get a value here of 1.018 times 10 to the negative 7 meters squared. Let me keep that in my calculator. So your length will equal that value times by your r, which we know is 1.5, divided by the rho. So it's going to be that value times by 1.5 and then divided by the 1.7 to the negative 8. And I get a reading here of 8.98 continued on. Now, let's just have a look here. I've got these are all two significant figures. So I'm going to make this so that would equal 9 meters would be my correct value. And because I'm doing it in two significant figures, I want to make sure that I show that I'm doing it, so I put 9.0 meters. It says the manufacturer of the resistor in A guarantees the resistance is within 10% of 1.5 ohms provided the power dissipation in the resistor does not exceed 1 watt. Suggests why the resistance of the resistor might be greater than 1.65 ohms if the power dissipation in the resistor is greater than 1 watt. Well, the reason for that is that the resistance increases, goes up with temperature. So with a greater power, we would expect greater energy loss, and that will cause the temperature to increase and therefore the resistance to increase. I hope you can follow that with my shorthand there. Show that for a power dissipation of 1 watt, the current in the resistor of resistance 1.5 ohms is 0.82 amps. Okay, so here we're looking at our power with resistance. Obviously, I'm going to be using these formulas. I'm going to be using the power is equal to I squared R, because I've got these there. Therefore, I is going to equal power divided by R, the square root of it. So I put that in, my I is equal to my power, which is 1 divided by 1.5, the square root of that. And when I do that, I should be getting a value of about a 0.82 amps. Okay, going on to this circuit question here now. It says the 1.5 ohm resistor is connected in series with a variable resistor R, which has a resistance of R, and a battery of EMF 6 volts and an internal resistance of 1.8 ohms. Estimate the resistance R of the variable resistor that will limit the current to 0.82 amps. So we're saying here that we have got a current in the circuit, if I have an ammeter, of 0.82 amps. Now, for this, I need to work on my total resistance. My total resistance would equal R plus 1.8 plus 1.5 ohms. So it would equal R plus 3.3 ohms. And I want my I, which is equal to V over R, to equal 0.82 amps. So I get 0.82 amps is equal to 6 volts divided by this value over here, 3.3 ohms, like that. And so when I do that, when I change the subject to the formula and so forth to do that, it's pretty straightforward. I'm going to get a resistance of 4.0 ohms.